The wolf population in the Upper Peninsula of Michigan, denoted UP, has been closely monitored since recovering from near extinction several decades ago. Okay, so here we are given two different rates. So this is one of the standard rate in and rate out problem where you're given two different rate of change. So here you're given the rate of change at which the wolves are being born, and there's the rate of change at which wolves are dying. So we're given these two rate of change that are really the opposites of each other. So I guess other possible variations that you might see, maybe the rate in is the rate at which you're producing some quantity, rate out might be the rate at which you're selling some quantity. Rate in can be rate at which maybe water or some other liquid or some material is entering some system, and maybe rate out is the rate at which it's going out. And rate in, another example of rate in might be marginal revenue, and rate out might be like marginal cost in the sense of economics. Anyway, going back to the question, let's quickly recap. The B of t is the rate at which wolves are being born. And here we're looking at t years after the start, after January 1st of 2010. So make sure you keep note of this 2010 years. And d of t is the complementary rate, and it's at which the wolves are dying out. So we're given the graphs of b of t, given right here, parabolic shape. And d of t looks like this. So what are the questions? Well, I guess there's a little more to say. Assume that no wolves are migrating in and out of the UP. So any wolf born in the UP is remaining there. So no one's going out, and no wolves born in some other place is traveling into the UP. So here, the rate in and rate out are completely controlled. So there's no other variables when it comes to the population change other than B of t and D of t. That's really what's happening here. So, and they tell us one more key information. W0 is denoting the number of wolves in the UP on January 1st of 2010. And this is a quite important information in some sense because you cannot figure out how many wolves there are at time zero by just looking at this. Because this graph is giving you like how quickly wolves are being born at time zero and how quickly they're dying out at time zero, that doesn't give you information about how many exact number of wolves at the very start. And this is really exactly the ambiguity with the constant of integration when you try anti-differentiating things. You need some initial condition, and that's exactly what W0 is giving us here. Anyway, before we look at the question, I want to quickly make a few comments based on D of t and B of t. So let me go back to the definition of D of t and B of t. And that's that because B of t and D of t, or rate of change, integrating them can actually give us some relevant information in change in some quantity. To see why, let's quickly remember one very important interpretation of fundamental theorem of calculus. When I have an integral from a to b of rate of change of some quantity, say like dt, maybe t is the time variable. For example, in b of t, we have the rate of change of the wolves being born, so that is our quantity here. And in d of t, the quantity is the number of wolves that are dying. But in general, when I integrate from a to b rate of change of quantity, then I get the change in the antiderivative of this from a to b. That's the fundamental theorem of calculus. And how do you anti-differentiate rate of change? Well, rate of change is the derivative. So when I anti-differentiate this, it's just that rate of change is gonna disappear, and we're just gonna get the quantity itself, and we're looking at the change from a to b. So when I integrate rate of change of quantity, we exactly get the change in that quantity from a to b. So for example, when I try integrating from a to b, b of t dt, since b of t is the rate at which the wolves are being born, we're going to get the number of wolves born from a to b. And if we try integrating from a to b, d of t dt, then similarly, we're gonna get number of wolves that die from a to b. And there's something even more that we can say. What about integral from a to b of b of t minus d of t dt? Well, there are many ways of thinking about this, but no matter how you see it, this is gonna get you the change in wolf population. One way to see this is to break down this integral into two parts, integral of b minus integral of d. And integrating b tells you the number of wolves being born. Integrating d gets you the number of wolves that died. So when I subtract the two, you should get the net change in wolf population. Another way to see this is by just realizing that this integrand, this b of t minus d of t that we're integrating, this is exactly the rate of change of wolf population. And the reason this is rate of change of wolf population is because B of t is the rate at which wolves are being born, minus you're taking away the rate at which wolves are dying out. So that's exactly gets you the rate of change of wolf population. So when I integrate it, I just get the change in population from A to B. So these are some key concepts to remember. Now let's actually try looking at the questions. So part A, write an expression that represents the total number of wolves born in the UP in the year 2017. Well, for this, let's quickly remember one more time that T here stands for the number of years after January 1st of 2010. So, for example, so if we think about 2017, the start of 2017, so like January 1st, 2017, this exactly corresponds to T equals to 7. And when 2017 is ending, so end of 2017, so this would be like 11:59 p.m. of like December 31st of 2017. I mean, this essentially just corresponds to T equals to 8. That's when you're moving on to 2018. So we're going from T equals to 7 to T equals to 8, so that might not be super obvious thing, so I just want to point that out. And you're trying to find how many wolves are born from T equals to 7 to T equals to 8, and we exactly know from above that you just have to integrate B of t dt to find the change in the number of wolves born from 7 to 8. So that's the answer to A. Let's look at B. Write an expression that represents the total number of wolves living in the UP on January 1st, 2018. So how many wolves are living there at 2018? Well, here, if you want to find the exact number, so you're not trying to find the change. If all you care about is the change in wolf population, then you can just integrate. But you're not looking for the change in population. You actually care about the exact total number. And for this, we need some additional information, and that's exactly this W naught that they gave us. So we know at the very start, at time 0, at the start of 2010, we are starting with W0 many wolves. And the question is, what's the change in population until 2018? Well, we just gotta figure out how much the population changed from 0 to 8. So we wanna integrate from 0 to 8. And as we said before, you wanna look at B of t minus D of t dt. So that gets you the answer to B. Let's look at part C. Is there a time t greater than 0 when the number of wolves in the UP was equal to W0? So here, they're really asking, was there a time where the number of wolves, where the change in population from time 0 to time t is 0? So number of wolves being born and number of wolves that died from 0 to t happened to be the same. So the population at that point was actually the same as W0. So is there a such time, and they want us to estimate the first, so make sure you pay attention. Maybe they'll put second or third. They want the first such time, and if not, they want us to write none. So let's go to the graph and see what exactly is happening here. And here I want to quickly give two more intuitions, graphical intuition on this. The first intuition is that whether D of t is higher than B of t or B of t is higher than D of t, it gives you information on whether the population is growing at the time or shrinking at the time. For example, from time 0 to roughly about the time coordinate up here, we see that B of t is higher than D of t, so more wolves are being born than wolves are dying. So here you have a population growth. Whereas the situation flips in this part of the graph. So here we have a population decay, where more wolves are dying than being born. And in the next part, we again have population growth. So that's one thing to keep in mind. Another thing to keep in mind is that this integral of B of t minus D of t, which gives you the change in wolf population, this is really the signed area between B of t and D of t, from A to B, I suppose. So what do I mean? Well, for example, if I look at this part, so if I look at this area between B of t and D of t, so right here, this area is going to give us the change in wolf population, but you have to take it with the correct sign. So area is always positive, but you're going to either multiply that by +1 or -1, depending on the correct interpretation. Here, the population is growing because B of t is larger than D of t. So here you should take this area with a positive sign. Whereas if you look at this region, then here, this area should be taken with a negative sign because you have a population decay. And the reason that this integral has anything to do with the area between B of t and D of t is for the simple reason that when I look at the area of B of t, well, area under B of t looks something like this. It's like this entire thing underneath B of t curve. And area under d of t looks something like this. It's like this part of the graph. So when I subtract the two, then you exactly get the area in between here. But definite integral, remember, it's not just the area, it also cares about the sign. So we actually have to take it with the correct sign. Anyway, armed with this intuition, I think now it's pretty easy to figure out the problem, which is whether there was a point after time equals to 0 where the population is the same as the initial population. So let's see. So from time 0 to all the way here, your population is growing and the population increased by this area. And now as I'm moving more to the right, so as like this area is getting larger and larger here, so as I'm accumulating more area like this, what's happening? So now the population is going down by exactly this area. So was there ever a point where population change is exactly 0? Well, that's when this green area exactly matches with the area for the population decay. So we know, like, say around, I'm not super sure, I think you just have to eyeball it. And I think around this point, say, we have that the green area and the red area are about the same. So at around this point, so I'm not quite sure where this is, maybe it's around like 1.3 maybe. So at around the time of 1.3, we know that's like the first time at which the net change in population from time equals to 0 is 0. So the population is W0 once again. To finish, let's look at part D. Estimate the times, so there might be more than one time, between 0 and 8, where the population of wolves in the UP was the smallest. So again, here we're not just looking for the first such time, we're trying to find possibly many different times where if the minimum population is reached at multiple times, you want to find all of them. So keeping that in mind, let's go back up. Well, when was the population the smallest? Well, here the population is getting larger, so that's not it. But we know over here the population is getting smaller, and when are you minimized? When do you get to the smallest population? Well, that's when you really subtract off this entire area with a negative sign here. So the population is minimized exactly at this point. And do we ever get back to this minimum population? Well, surely not, because here we have a population growth again. So population is just increasing to the right of it. So there's only one point at which we get the global minimum for the population, and that's around this point. I guess that's around like 4.8, 4.7. So let's just say 4.7. So going all the way down, the only point that we want is around 4.7. I'm sure if you're off by a bit, since all day one is an approximation, you should be okay. Anyway, that concludes part D.